All right, so before we had the electric field due to a bunch of charges. So let me just kind of put all this together. We had point charges. So there was like a point charge here, maybe it was positive, and maybe there was another positive point charge over here. And then we could find the net electric field at this point P. That net electric field would look like a positive test charge would be pushed away, so there would be an electric field this way. This guy right here would create an electric field that way. And so with single charges, we would find the electric field due to each one of them and then find the resultant. Then we extended that and we took a whole bunch of positive charges and smeared them along some rod like that, and we looked for the electric field at that particular point, and it was the sum. So there was an electric field due to this one, an electric field due to that one, an electric field due to this one, an electric field due to that one, like that, and it's getting a little bit bigger, and something like that. There we go. Kind of looks like a fan, where the x components were canceling each other out, but ultimately we found that the electric field was the sum of k dq over r squared r hat, which meant that there was a direction. Does that seem familiar? Okay, so just like we have an electric field at a point due to point charges, if I have my little positive charge here, my positive charge here, I can also find an electric potential at that point. Now electric potential, V equals KQ over R, is a scalar. It's not a vector. So either there is electric potential and it's positive, or there's electric potential and it's negative, or there's no electric potential. I generally think of electric potential as looking like mountains and valleys. So, for example, this guy is positive, this guy is positive, and I think about that as being maybe something like this, but then as I get closer to that one, it doesn't go all the way back down to zero. Let me do a better job. It doesn't go all the way back down to zero because there's positive potential and positive potential there. And then we'll go to zero like that. So that's kind of how I think of electric potential. I think of it almost in terms of graphing this function and moving those graphs close together. Now, what if I had a negative charge? So we have a positive Q here and a negative Q there. Well, I think of this as being my positive mountain here, and it would reach probably zero because then, woo, we go into like a valley, like that. Where if these two were exactly equal in magnitude but opposite sign charges, where would the electric potential be zero? In the middle. So right here at the midpoint, our electric potential would be zero. If they are different size charges, so we've got a plus Q here and a minus 3Q over there. So we might have a mountain like this. What's my valley going to look like? Probably deeper, bigger, something like that. So where's the electric potential going to be zero? Yeah, probably somewhere over here. Okay, so that kind of gives you an idea. That's how I visualize this positive electric potential and negative electric potential. Now, what if instead of point charges, though, we have a whole bunch of charges again? Like a whole line of positive charges. Now, it's not a vector, so I'm not going to be drawing arrows, but there is an electric potential due to this guy at that point P. There's an electric potential due to this one here. So we would have, if I could chunk these charges that are on this line into, you know, charge 1, charge 2, charge 3, charge 4, charge 5, charge 6, 7, 8, and 9, the net, or the sum, of the electric potential at that point would be the electric potential of charge 1 and the electric potential of charge 2 and the electric potential of charge 3 and so on. But what's changing about each one of these charges in point P? The distance is changing. So I could find the total electric potential by summing up the electric potential contributions due to every little bit, every dq over r. But it's no vector, so there's no r hat. So let's see if we can apply this. Let's try an example. Let's say that we have a ring of charge. So we're going to find the electric potential at point P of a ring of charge. So remember, I'm a terrible artist, but just bear with me. So here is my ring of charge. Something like that. Here is that center axial line. And let's throw point P out here. Does this look familiar? Have we found the electric field at point P due to this charged ring before? We summed up all the electric field contribution. So now we're going to sum up all the electric potential of all these charges. And we'll say this distance from the center point of the ring to point P is x. Let's let the radius of our ring be a so that our r's don't get all difficult. Now, just like when we did the ring for the electric field, all the dq is exactly the same distance away from point P. If this is P, right there, aren't all the little bits of a charge the same distance from P? So the electric potential would be the sum of K dq over R. What's R? R is the distance from a little bit of charge on the ring to point P. What would that be in terms of my given bits of information? So we use that Pythagorean theorem, good stuff. And what's the integral of dq? As we go around, we go from 0 to the total charge on our ring. Limits are good, sorry. So kq over a squared plus x squared. And that is it. Now, what if I ask you to find the electric field next? How is the electric field related to the electric potential? From yesterday, the electric field was negative partial derivative of the electric potential function with respect to S, the 3 dimensions, or up to 3 dimensions. So can we take the derivative of this with respect to x, y, and z? Yeah, let's do that. So the electric field in the x direction would be equal to negative dv dx. Oh, what would that be? So negative kq over what? A squared plus x squared. Is that raised to the 3/2 there? Let me start over here. I'll do this. So we're going to take the derivative of, I'll use some old school notation eventually. Okay, KQ times a squared plus x squared raised to the negative 1/2. So what's the derivative of that guy? We have negative times negative 1/2 KQ times a squared plus x squared to the 1 less power, which would be negative 3/2 times what, 2x? Okay, so then what does that simplify to? My half and my 2 will cancel out. The negative and times a negative would be a positive. So what do we wind up with? KQX over a squared plus x squared raised to the 3/2. Look back in your notes. What was the electric field at the center of the ring? So pretty cool. We can find the electric field by taking the partial derivative of the electric potential. Let's try another one. Let's try a uniformly charged disk. So we want to find the electric potential at point P. For a uniformly charged disk. Again, I'm going to do a horrible job of trying to draw a disk here. So this guy's solid. It's not a ring this time. I'll color it. My charge is yellow. Today. So again, we have point P out here, a distance of x from the center of my disk. And let's let the radius of our disk be A, just like before, but not a ring, it's a disk. Questions so far? Okay. So, the electric potential at this point is due to all of the little bits of charge all over this disk. Are all those little bits at the same distance from point P? Not this time. It's going to depend on where we are, at what radius, at what piece of A, okay, piece of the radius that we are from the center of that disk. So if our electric potential is the integral of K dq, because we're adding up all of the electric potential due to all the little bits of charge, over R. Now let's look at a bit of charge. I don't have anything drawn down here, so I'm going to look at a little chunk of charge right here. That little chunk of charge is a distance R from point P, and it's some distance from the center there. Now, if our charge is uniformly distributed, that means that the charge per area is constant. Or that dq over dA is sigma. So let's make a dq substitution just like we did before. So K would be what? Or dq would be sigma dA. We need to come up with an expression for the area, a little bit of the area. How can we make a disk? What geometric shapes could you put together to make a disk? A bunch of circles, a bunch of rings. So let's say that dA is the same thing as 2 pi r dr. What do you think so far? So then our electric potential, we're summing up 2 pi r dr over r. Did I do that correctly? We have too many r's. Let's make this one capital R as the distance from this place to that point right there, and the radius of our disk, our variable radius of our disk is r. So this stays as little r, that stays as little r, but this needs to be capital R. Okay, pretty easy little change there. Any questions about that? Sorry. So what's capital R? Doesn't it depend on where we are? Yeah, isn't it like the square root of r, the distance from the center of the disk to some point dq squared, plus x squared, the distance from the center of the disk to point P? So r squared, this is x squared, so this would be capital R squared. So let's make a substitution. You can pull out constants if you want to. Yay! So let's say u is what? R squared plus x squared. So then du would be 2r dr. So this is a bunch of constants up here, but effectively we would have the integral of du over the square root of u, which would be what? 2u to the 1/2. So then my electric potential, we need some limits. Does our disk go from 0 to A? Yeah. So we have K stays there, sigma's there, pi is there, and then we've got this 2 times u, which was r squared plus x squared, raised to the 1/2, evaluated between 0 and A. Oh, can I put the 2 out in front? Is that okay? Over, I'll do it one step at a time. So we'd have a squared plus x squared, 1/2, minus x squared to the 1/2. Did I do that correctly? So then 2k sigma pi times a squared plus x squared, I like a square root function, minus x. So now that we have the electric potential function, let's find the electric field. We'll have negative dVds, partial d. Bless you. So my electric field in the x direction would be negative dVdx, which would be negative d dx of 2k sigma pi times the square root of a squared plus x squared minus x. Don't we have to use some sort of, oh, these are easy. Negative 2k sigma pi times, what would that be? 1/2 a squared plus x squared times 2x. Negative 1/2 right here, thank you. And then minus 1. So let's see, we'd have negative 2k sigma pi times x over the square root of a squared plus x squared minus 1. Or 2k sigma pi 1 minus x over the square root of a squared plus x squared. That's still for the electric field. What was the electric field due to a disk that we determined like a month ago? How cool is that? So if you can find the electric potential, in a lot of cases, it doesn't work always because of the nature of the problems. We can find the electric field of the electric field at the point too.